Today we've got some fun stuff. We're gonna get into troubleshooting. We're gonna do some psychometrics, so some of the air side of things. That's just a fancy word that means the study of air. Matt's gonna talk a little bit about airflow measurement and some duct modifications, some things you can do in the field. Again, like I've mentioned, I'm really tailoring this to technicians, apprentices, installers, people who actually are field active, not necessarily folks who are designers or that sort of thing. So we're not going to talk about like manual J, manual D, load calculations, that kind of stuff. We're going to focus on things that you can actually affect in the field. Today there's going to be a mix of some basics. So some of it's going to be like, yeah, I already know that, and then we're going to get into some stuff that's pretty advanced that you may not even necessarily be practicing that much, but this is going to be really helpful for you, especially when you're trying to troubleshoot and deal with moisture issues. Mold, high humidity, that kind of stuff. So we're going to try to do a mix of both. But we're going to start with just basics of troubleshooting. Being a good troubleshooter, being a good diagnostician, being a good technician. Okay, so I want to get a couple of you, and if you don't raise your hands to answer these questions, I'm going to call on you here, okay? So I want you to identify, what do you think are the characteristics, so the kind of the core personality traits, the ways of being that make for a good troubleshooter? What does it take to be a good troubleshooter? That's the question. Patience. You have to be able to think outside of the box. That's good.
Get to the understanding of the reason why how things work.
Yeah, first principles, how things work, a deep understanding of what's actually happening.
Observe the situation properly.
Be able to observe the situation, that's good.
Follow the process, like a step-by-step.
Be able to follow a process, yeah, for sure. What changes? Yeah, that's good.
Consistent approach.
Having a consistent approach, I like it.
Knowing the system.
Knowing the system.
Work or it should work.
Yep. Fundamentally understanding how it should work. Sequence of operation, knowing something about it. Yeah, that's true.
Safe approach. Safe approach.
Having a safe approach, yeah, for sure. Good. Yeah, a lot of really good stuff there. So, what's that? Consulting the manual, being willing to read, being willing to. One thing that I think is a really tough balance for a troubleshooter or a good technician is the ability to second guess yourself an appropriate amount, right? So I'm going to talk about that for a second. What does it mean to second guess yourself an appropriate amount? Think about that. Because if an overly confident person never says, hold on a second, right? They just say, nope, this is what I do, right? Because like you mentioned, process is really important. Having a systematic approach is very important, and it actually is helpful with not making you second guess yourself. But what does it mean to second guess yourself an appropriate amount? I want to hear from you. Go ahead.
Being open enough to change your thinking when it's necessary.
Being open enough to change your thinking when it's necessary. That's really good. I like that. So for me, one thing that I found really good technicians, really good troubleshooters have in common is that they leave their ego aside, right? The goal is to come up with the correct answer, right? That's the goal. Nothing else really matters. And one of the key things, and this is true in like everything, there's a term called super forecasters, okay? And these are people who are really good at being able to figure out what's going to happen in the future. And they've done a study of these people, so it's like market trends, that kind of thing. And what makes these people really, there's a whole book about this and the study that was done around this. What makes them really good at being able to understand what's going on, basically. What's going on in society, the economy, all that sort of thing. And there's a single trait that makes a really good super forecaster. And that's the ability to change your mind and your beliefs based on new information. New information comes in, you can say, it doesn't matter what I thought before. If this new information is better and is proven to be better, then I accept this new information, right? And I'm going to apply it. That's open-mindedness is really key.
Yeah, the way I think about it is like you're building a case for your diagnosis, right?
Yeah.
So then you're like, oh, you know, maybe it's a unit like, oh man, these units, it's always the contactor, right? Or something like that. But yeah, or it's always the float switch, right? But if there's a piece of data that you encounter that conflicts with, you know, the case that you're building for that, then you need to figure out why that is. How does that fit into this case that I'm building, right? I can't just be like, well, I'll just throw that aside, right? Like, because you're going to be back if you do something like that, right?
That's a really good point, because process of elimination, that's a term that really applies well to troubleshooting. You eliminate possibilities based on the facts present. The challenge is that your prerequisites in your data are really, really important. So one of the most common, I'm going to ask this to the senior techs in the room, okay? I'm going to be the junior technician. Junior technician calls you up, and I don't know how you guys talk when you call each other, and where I'm from, Groveland, Florida, that's where I was born and raised. You got these guys, and they come up and say, hey man, this unit's doing something weird. And then they stop talking. Right? And so then what do you have to say? What's it doing, man? Oh man, my pressures are all over the place on this thing. And then they stop talking. Well, what do you got? You got head pressure, suction pressure? Yeah, man, I don't know. Like, I hook up to this thing, and my suction pressure is 0, and my head pressure is 420. What's your suction temperature? I mean, like, is it, like, what? I don't know, man. Do you think this thing has the wrong Freon in it? What? What are you talking about? Right? And so do you see the problem with that way of thinking? The problem is that you're not committed to gathering data and process elimination. And I can tell you that particular call I've received probably 50 times over the years, and it's a version of that, and it's literally because they either have the hose hooked up backwards, so that way the Schrader's not being depressed because there's no core depressor on the one side, or it's just not screwed on far enough, so it's not pushing the core in. And so they're reading 0, and they're like, or they'll do the thing of, man, I put like a bunch of Freon in this thing and ain't nothing changing. I'm like, what? Did you use a scale? Like, how much did you put in? No, I don't know, I just put a bunch in and ain't nothing changing. I'm like, you don't put a bunch of Freon in and ain't nothing changing. That doesn't work. I don't know what you're talking about. So, and again, I'm not making fun of anybody who's new, because I get it. Like, I understand how that happens. But troubleshooting is all about gathering data and then making sense of that data. What matches? What doesn't match? Right? It's like, I don't know if you guys watch, like, the kid shows when you're a kid, but like, one of these things is not like the other. Like, one of these things doesn't fit in this puzzle. And so why is that? And when you see something, like in that particular case, when you see something that doesn't make any sense whatsoever, like this makes no sense, then often it's your tools, or it's like some way that you have something connected, or it's something, and you second guess that. You're not second guessing yourself every time, all the time, right? You're following the process, then all of a sudden it's like, hold on. This doesn't match. I'm not going to call somebody right now because what I'm about to give them, I understand, is a senseless pile of goop, right? So I'm gonna try to establish, all right, am I actually connecting to the Schrader here? Is it actually pushing in? And that's where, understanding your tools, and that's why I always go back to, like when we talked about your vacuum pump and your leak detector and your multimeter, and those tools that like you have to use all the time, your probes, your gauges. You really, really need to understand those tools. You need to understand the care and maintenance of those tools. So please pull out the manual, just get to know your tool. Because I assure you here, like, you guys don't all have exactly the same tools, right? It's very rare in a company for everybody to have exactly the same tools. So you have to take some ownership of, this is what I've got in my van, understanding how that works. And that's a big part of it, but that's only one part, right? There's this entire stack of things in order to be a good troubleshooter that you have to understand. And as we kind of go through this, we're going to talk about some electrical, we're going to talk about a lot on the refrigerant side. But understanding that we expect a lot out of technicians. We expect you to understand a lot of different things. We're going to talk about psychometrics today. We're going to talk about airflow. We're going to talk about electrical. We're going to talk about refrigerant cycle. And that is a lot for you to understand. So you also have to be realistic about what you know and what you don't know. I have to be realistic about it all the time. He asked me to remember what this symbol means. And I'm like, oh, see, you misunderstand. I don't know a lot of stuff. Like, I speak confidently about what I do know, but I've forgotten a lot of things over the years where I'm like, if I saw this on a schematic, I would go down to the legend and be like, what is that again? Like, oh, okay, that's what it is, right? One of the most extreme examples is we were doing a live stream. Matt and I were doing a live stream the other day, and we were actually talking about trapping and refrigeration, so trapping of refrigerant lines. And somebody said something about an inverted trap, and I was like, hold on, is that right, what I'm about to say? And so literally, we're on the live stream, I open up another window, and I open Google, and I just check real quick, just like, what is that? And then, you know how nowadays Google gives this like stock response, like from the top? Well, it gave this response, I was like, oh, okay, that's right. And then I looked down at the source, and the source was HVAC school. It was something that I had written, that it was drawing from. And I'm like, I need a reliable source, not this idiot. I need somebody who knows what they're talking about. So the point is that it doesn't matter how long you do it. It doesn't matter how good you get, because there's so much information. And the further you go down the path, the more information opens up. The more you realize what you don't know. That's that idea of the Dunning-Kruger effect. When you first learn something, you get really confident. They call that Mount Stupid. You think you know everything, right? And then as you learn more, you realize, oh crap, I don't know anything. This is really complicated. And then you kind of climb your way out of it again, where now you actually gain real knowledge, but you see how big the base is and how complicated all these things can get, and you get a little humility, right? So, back to the basics here. Always being willing to take in new information, and when you come up with new information that changes your previous assumptions, be willing to, and it's proven to you, be willing to accept that new information. Right? Make sense? Everybody can agree to that? Good.
Hey, Bryan. Did you ever have this happen to you? I know for us kind of old guys that have been in the trade a long time, I tell this story and I don't think people believe that it's true, right? You'd be sitting behind the unit. So for me, I've been sitting behind the furnace, been in the business like 6 months, call my boss, hey, this thing isn't working. Did you check X? Yes. X? Yes. X? Yes. And I'm going through what I checked, telling them all my readings. Did you check X? No. Click.
Click, yeah, right.
Right. And so I think for us, we benefit from having all the knowledge, but I think sometimes we have too much
Right.
At our fingertips. Right? If I was sitting behind that same furnace today, I'd probably just Google exactly what it was, and I'd go straight to that source and fix it and get out of it.
Yeah.
Right. So I think it's always good, whether we're in service, sales, whatever it is, to have a process so that we know where we got lost.
Yep. Yep, really good. Good, Jerry.
So one of the things I do, I saw some of this on one of your guys' videos. I think it's Bert and Elliott running through some of the basics, and they were talking about how you can figure out a lot from those. I think they call it the 5 pillars.
Yep.
One other thing I asked the guys whenever they call me over the phone for something along those lines, they go about the suction pressure, discharge pressure, line temperature, those 5 basics to your delta T. Also, just add to that, do you have an expansion valve? Do you have a
Yep.
piston? And then we just start from there and
Yep.
move on. But I try to get that much information before we go much further.
Yep, for sure. On the refrigerant diagnostic side, and that's actually what we're going to dive right into now. But yeah, to your point, you do need to know what the metering device is nowadays, for sure. And then obviously you go beyond that. Is it a communicating system? Is it an inverter-driven compressor, multi-stage, all that? You got to eventually know. And I'm just going to kind of, again, a lot of these things are rules of thumb. This is something that comes up a lot. People will come up and ask me like, hey, there's this specific unit that's doing this specific thing. And I love to try to help people solve those problems together. But the stuff I'm going to talk about is going to be more general. It's like the building blocks that you can then, build the rest of your troubleshooting skills off of. But I want to also talk specifically about what the process is and how to change the process so you can become a better troubleshooter. All right. So we're going to talk about the 5 pillars. We're going to talk about wide, narrow, wide diagnosis, and we're going to talk about isolation diagnosis. Those are kind of the 3 things that I cover a lot that will hopefully make you a better diagnostician, better troubleshooter. So in addition to these 5 things, the 5 pillars, which I realized later on, has anybody ever heard 5 pillars before? Apparently there's the 5 pillars of Islam. I didn't know that when I first created the 5 pillars, and somebody brought that up to me. That wasn't intentional. I'm not trying to co-opt. So suction pressure, head pressure, superheat, subcooling, and delta T are what I call the 5 pillars. Now, again, I wrote these 5 pillars back in about 2002, 2003. When we were in R22, I was working for a different company. If I had to rewrite them now, I would probably not even necessarily say superheat and subcooling. I would more just say liquid line temperature and suction temperature, because then those correlate, right? So when we say head pressure and suction pressure, I'm going to start there. To start there, basically. When I say suction pressure, what am I really saying? When I ask for suction pressure, when you ask for suction pressure, when you communicate suction pressure, what are you actually communicating? Simon jumped right to it, and he's cheating a lot because he's listened to me a little too much. So most people will say, okay, suction pressure, well, it's suction saturation temperature, right? SST. So you take the pressure, and on the old gauges, you would look at the needle, and it would point to, based on the refrigerant you're working on, or on the PT chart, that is the saturated suction temperature. But let's talk about what that means, what saturated suction temperature means. And we're gonna let me see here. Yeah, there we go. We'll jump forward into this. So what does that really mean? What does that really signify? I'm going to call on one of you if you don't answer. Romain, what does suction saturation temperature really signify?
It's the change of state of the refrigerant.
The temperature at which the refrigerant is changing state at that pressure, right? But this is where a lot of guys get confused, because this whole PT relationship, pressure-temperature relationship thing, it's like, well, yeah, but my pressure's this. That means the refrigerant is that temperature. No. It means the refrigerant is that temperature if it is in the process of changing state. And the way that I say it is, it's when liquid and vapor are present at the same place at the same time. At the same place at the same time. So when you are measuring a temperature that is the same as the saturated suction temperature, so if you hook to your suction line with a clamp, and you look at that pressure, you look across the needle, or you look at the gauge, and it's the same, what do we call that in terms of superheat? There's a term for that. We call that zero superheat, right? So when you have zero superheat, your line temperature, your suction line temperature matches. Let me grab one of your probes here real quick, just so we can kind of make sure that we're holding that up. And all right, so if what I'm measuring in pressure, and that correlates to a temperature, matches what this clamp reads on the suction line, that's telling me that we have liquid and vapor present at that point. If I'm measuring the pressure and the temperature at generally the same place. Does that make sense? So in your suction line, for example, coming back to your compressor, is that a good thing? If I'm reading saturation, I'm reading that I have liquid and vapor present at that place at the same time. Is that a good thing in an air conditioner? No. Why? Why isn't that a good thing? You don't want liquid going in the compressor. We call that flood back, right? So liquid's going back to the compressor. The compressor does not pump liquid. The compressor is a compressor. It compresses vapor. It does not pump liquid. It's not designed for that, right? So if you put liquid into a compressor, parts start coming off, and that's not good. So that's not a good thing. So understanding that is really important. But to go to what Simon said, I like to go even beyond saying that suction pressure is suction saturation. I like to call it evaporator temperature, because that's really what it is. When you look at that pressure and it correlates to that temperature, that tells you what the temperature of the evaporator is. In refrigeration, that's all we call it. We don't even talk in terms of suction pressure generally. We'll just say evap temp. What's your evap temp? And if that correlates to 35 degrees, you say 35 degree evap temp. That's what I've got. Now here's the trick. Is that entire evaporator coil 35 degrees? No. What part isn't 35 degrees in the evaporator? The last part, right? The top part, right? So you feed it in the bottom. You feed this saturated, boiling refrigerant. I always wish they would call evaporators boilerators. I think that would be cooler, and that's actually more accurate about what's going on. The refrigerant's actually boiling in that evaporator coil. You have boiling refrigerant in the bottom, and it boils until it gets to the top, and hopefully the last little bit is fully vapor. And whatever temperature's picked up in that vapor, that's what we call superheat, right? Make sense? So what are we measuring when we measure suction pressure? Again, I'm just going to make you say it again, and so what are we measuring when we're measuring suction pressure? We're measuring evaporator temperature. That's what we're looking at, right? So that tells us our evaporator temperature. Now in our market, or this market, my market, why is evaporator temperature like really important to us? We know that we don't want to get below a certain number in our evaporator temperature. What is that number we don't want to get below in our evaporator temperature? 32 degrees, right? Now, here's an interesting thing. You're measuring the temperature inside the evaporator, right? So you can actually get a little below before it starts freezing. So like 31, 30 in that range before it starts freezing. But once you get to that point and it starts freezing, all bets are off. Why? Why are all bets off as soon as it starts freezing? No air's going over the evaporator coil anymore, right? And that evaporator coil relies on that heat from the inside to keep that suction pressure up, right? It needs heat. It needs to be fed with heat. The evaporator is the heat absorber. With this group, I'm not going over the basic refrigerant cycle. We're doing that with the apprentices, right? So if you're like, I don't know what you're talking about, we'll go over it again this evening. But for you guys, you understand, the evaporator is the part that absorbs heat. It picks heat up. It's the heat absorber. And so as soon as you get a sheet of ice on that sucker, well, now you've ruined its ability to pick up more heat. So now that suction pressure just dives on you. So we have to keep it above 32. But we don't want to get it too high for obvious reasons, right? Like obviously if the evaporator coil is too warm, it's not going to absorb heat. But in this market, we also don't want to get it too high because then it's not going to remove moisture very well, right? It's not going to pull moisture out. So we have to kind of do this dance. And that's where, generally speaking, under normal conditions, we try to keep around a 40-degree evaporator because it's sort of the safe zone, right? It's far enough away from 32 that we're not going to freeze, and it's not like a lot of evaps nowadays try to run 45, 46, 47. If you run 400 CFM per ton, we would like to keep it a little colder than that because that means we get more moisture out of the air, right? So that's why understanding this evaporator temperature thing is really important. We got to understand that. Now let's talk about just, again, some of these rules of thumb. Generally speaking, about 35 degrees below your indoor temperature is what your saturation is going to be at 400 CFM per ton. So let's just do that math. And again, it's actually a little more than that with modern coils because they're bigger, and so you're going to see a little bit higher. But we want to keep it in that range, if not a little bit lower. So if it's 75 degrees inside, what should your coil temperature be about, plus or minus 5 degrees? 40 degrees, like we just said, right? If it's 75 degrees inside. Now, if you walk into a house and the air hasn't been working and you just started it up and it's 90 degrees inside, what should the evaporator temperature be thereabouts? 55, right? Pretty simple. 15 degrees higher than 75, right? However you do the math, doesn't matter. If you got to pull out your calculator, nobody's going to judge you, right? It's okay. That's what it should be. And that's important to know, right? Because if you're a new tech and you're like, oh man, I'm used to a 40, this thing should have a 40-degree evaporator coil, right? And you go and it's 55, you're going to be like, why is it so high? And you're going to think it's a problem. Well, it's not necessarily a problem. It's tied to that indoor air temperature going over the coil. It's actually beyond that, though. The fact that we have so much moisture and so much condensation on that evaporator coil, our dew point is so high, that actually drives up our evaporator temperature a little bit. So we actually run higher evaporator temperatures because of that. It's sort of a chicken and the egg problem. It's like we want our evaporator temperature to be low because that helps us pull more moisture out, but because we're pulling more moisture out, it actually holds our evaporator temperature up, right? So it's like this tricky issue that we face. So all said and done, if we can get close to a 40-degree evaporator coil at 75-degree indoor temperature, we're good. Now, this also tells us something, though, because you get these clients in this market. Do you have clients who like to set their air to 65 degrees inside the house? So do the math. 65 minus 35 equals what? 30, which is below 32. Right? Now here's the thing. Does a coil freeze because the client sets the thermostat too low? No. The coil freezes because the house gets too cold. Right? So the fact that somebody sets the thermostat down too low doesn't matter unless the house actually gets that cold, right? And that's a common misconception. Guys will go in and they'll be like, oh, well, the reason why the coil froze up is because the customer set it at 65 degrees. Well, hold on a second, because if it's a really hot day, that alone doesn't cause it to freeze. Does that make sense? It's if it actually is able to get there. It's all about the air moving over that coil and the temperature and enthalpy, overall heat of that air that matters. That's what we call load. Load on the coil. Have you ever heard that before? What's the load on your evaporator coil? It's high load. That means the air is real hot, right? Low load. That means the air is real cold or you have poor airflow. That's all that means, right? High load means you're giving that evap a lot of heat to work with. Low load means you're not giving it very much heat to work with. And low load is a problem because we hit freezing. If we didn't have issues with water freezing, well, man, we can make it as cold as we wanted. It all comes down to the water freezing issue, right? And that's why in refrigeration, we have to have defrost. We have to have a method to get the ice off because we have to accept the fact that there's going to be ice on the coil. You know, think about it. If you're trying to keep, you know, a box at 0 degrees Fahrenheit, well, then you have to have an evaporator coil that's colder than 0 degrees Fahrenheit. You might have a negative 20 degree evaporator coil. So it's going to get ice on it. So you have to have defrost to get the ice back off. The problem in air conditioning is we don't have an indoor coil defrost system. So we just have to keep that coil above 32. Does that make sense? Now, clients get real cranky about this sometimes. Because they're like, I'm a billionaire. I should be able to set my AC to anything I want. And it's like, maybe your mother should have spanked you more as a child. Like, have you ever thought about that? Don't say that to clients. I saw Shay make a face there. It does require some conversations sometimes to help the client understand. It's not what you set it to that's the problem. It's that it will freeze once it gets to a certain temperature inside your home because of how all air conditioners, residential air conditioners, are designed, right? There's not really I mean, you could design a system that didn't freeze, but it would then not dehumidify well. Like there would be this whole issue there. So understanding this is really important. Does that make sense to everybody? So you can always know when you walk up to a house pretty much what that saturated suction temperature, what that evaporator temperature should be when you walk up to a house. You should pretty much know. If you look at the thermostat, and again, ideally you should measure the temperature in the return, and that would be what you base on. But if you look at the thermostat and it's 75 degrees in the house, or 78 degrees in the house, or 80 degrees in the house, or 85 degrees in the house, subtract 35, going to be pretty close, right? I'm going to ask this to you guys, though, those more senior techs. Do you see it a little higher than that? Like, are you seeing evap temperatures that are a little bit higher than that? And that's what we see, too, because evaporators have gotten a lot bigger. And so I'm talking in an ideal world, you may see that that number is more like 32. In some cases, even 30, but that's not great, right? Because that indicates that we aren't running cold enough coils to do a really good job of dehumidifying. So that should be an indicator to you that, right? Even if you look at a ductless system. If you look at a ductless system and just for fun, you hook up one time, hook up to the suction side, and just look and see what your evap temperature is. And if it's significantly warmer than that 35 degrees below indoor temperature, it's not going to dehumidify well, right? We're going to talk about this later today, but pulling moisture out of a house takes two things: cold coil and long run time. That's it. There's no other magic. Cold coil and long run time. So if you make it run a long time and it's got a cold coil and it's big enough, it's going to dehumidify really well. Now there's other things that can go on in the house that aren't the air conditioner's fault, and we'll talk about that too. Possible causes of improper suction pressure. I'm not going to read all of these to you. This is part of, we have all of this that exists in the app. Some of you were showing me the free app. You can go through and get all of this. Jerry's a king of this stuff. He knows all this stuff really well too. But there's all these possible causes, and don't just assume that it's always one thing. Like guys they'll start to get, it's low on charge. Suction pressure's low, it's low on charge, right? No, that's no. If there's one thing I can beat into your head, do not charge by suction pressure. That is not how you charge a system. Now, if you walk up to a system and you're running like, I don't know, 5 degrees suction or 5 psi suction, which would be like a negative something, negative 35 degree evaporator coil, and you go up and you grab the suction line and it's warm, well then yeah, the thing's flat, right? Like, so you don't have to do further troubleshooting at that point, right? You pretty much know. Again, I say that, but that's not even necessarily true. Don't charge by just suction pressure. Always gather all of this information before you make a diagnosis. Head pressure. So when I say head pressure in a residential context, what am I actually saying? Am I saying discharge pressure? I'm talking about liquid pressure, right? So I'm talking about liquid line pressure. So it's coming from that indoor unit, right? That's what I'm talking about, or going to the indoor unit. I'm talking about liquid line pressure. I'm not talking about discharge pressure. Those are not the same. They're both on the high side of the system, but discharge pressure is which line? What does the discharge line go between? What two components? From the compressor to the condenser coil, right. And what is in the discharge line? What? Superheat. High temperature, high pressure, superheated vapor. Right? So it's all vapor. 100% vapor, real hot. Don't go touching discharge lines. It will burn you. It's warm, right? And again, when you look inside of a condenser, that's the line coming right out of the compressor, going into that condenser coil. Right? That's the discharge line. Is that where we measure our pressure? No. So when I say head pressure, I'm not talking about the discharge pressure. Now, if I was talking about in a refrigeration context, when I said head pressure, that's exactly what I'd be talking about. Because if I meant liquid pressure, I would have said liquid pressure, right? So this is where words become really important. If you find yourself ever working on a package unit, for example, the only port is generally on the discharge line. So you got to know that those are two different things. We're talking liquid pressure. But what are we actually talking about when we're talking about liquid pressure? What do we really care about? Care about subcooling. We're trying to get to subcooling, but this is just like everything on this side is like the suction side, but flipped, right? So what are we looking for? So if we're looking for evaporator temperature with our suction pressure, we're using our suction pressure, but really what we care about is evaporator temperature. What do we really care about when we're measuring liquid pressure? Not temperature of discharge, because we're not measuring in discharge. Condensing temperature, there you go, bam, condensing temperature. We know the condensing temperature. We know what temperature at which the refrigerant is condensing, okay? So, when I take this, okay, and I put them together on the liquid line, so here we go, liquid line, and I'm measuring the temperature here, and the temperature here equals the saturated condensing temperature, condenser saturation temperature, liquid saturation temperature, and they're the same. What do we call that? Zero subcool. Is that good? No, because what does it mean? You don't have liquid, right? It's still, because again, whenever the saturation temperature matches the actual temperature, that means you are at saturation. And what does saturation mean? Liquid and vapor at the same place at the same time. Right? Do we want liquid and vapor at the same place at the same time in the liquid line? See, it's amazing how they name these things. It's the liquid line. What do we want in the liquid line? Liquid, right? And what does subcooling tell us? Whether or not we have liquid, right? Subcooling is basically a mathematical sight glass. You ever seen a sight glass before where you can look and you can actually see that it's fully liquid and there's no bubbles? Subcooling is just we're using math to tell that it's fully liquid in that line, right? And that's really important, because if we feed our metering device with something other than fully liquid, then our metering device cannot do its job. Our evaporator cannot feed properly. It is not designed for that. So we have to have a full column of liquid. Talk a little bit about the condenser. We talked about this yesterday, and it's just a quick refresher. Vapor comes out of our compressor. It goes into the top of our condenser coil as fully vapor. The first little bit, it's dropping temperature fast. It might go 210, 205. It's dropping until it hits that condensing temperature. And then that's the bulk of what happens in the middle of the condenser. If you take a thermal imaging camera and you look at a condenser coil, what you're going to see is real hot, temperature drops, it gets to the center, stays the same temperature. It's just like that boiling pot of water. Boiling pot of water boils at 212, right? It stays the same temperature as it's condensing. That's our condensing temperature. That's our liquid saturation temperature, or our whatever we want to call it, high side saturation, whatever you decide to call it. It's condensing temperature. And why do we care about condensing temperature? Why does that matter to us? Because we can compare it to outdoor temperature and we can tell if it's normal or not. If it's elevated, that's not a good thing, right? I'm going to pause quickly and talk about one of my favorite topics, which is compression ratio. Okay? That's a fancy term. I'm not even going to tell you how to do the math because I do not care. how to do the math. It does not matter to me right now. But here's what you need to know. When your head pressure is high or your suction pressure is low, see, look at this, low and high. See how they get further away from each other? That is a higher compression ratio, right? Let's draw this on the whiteboard here. Because this is not complicated, all right? So we got one system here that's running 110 suction, and we're going to say 450 psi head. Okay, then you have another system that's running 145 degrees suction, 145 psi suction. This is literally super stupid what I'm doing right now, but I'm just wanting to show you this, okay? Which one has a higher compression ratio? You don't have to know much. This does not take much thinking. It's the one on the right, okay? Why? Because there's a bigger difference between this and this, right? Versus this and this. Which compressor has to work harder? This one or this one? The one on the right? Which system is going to perform better in terms of capacity, BTUs? Which one's going to move more BTUs? This one. Which one's going to move less? This one, right? Which compressor is going to run hotter? The one on the right. Which compressor is going to last longer? The one on the left, right? Really, really simple. Super simple. So what is one of our main jobs to do to get more efficiency? And there's a caveat to this, which I'll give you in a second. To get more efficiency out of a system, which is lower head pressure and higher suction pressure, right? Lower head pressure and higher suction pressure equals less work to move BTUs. There's a problem though, because what's the problem with higher suction pressure? We just talked about it. Higher suction pressure means a warmer coil. A warmer coil means less dehumidification, right? Because in order to dehumidify, you need cold coil, long run time, right? So that's the problem with us, is that you have to trade efficiency for dehumidification. They get less efficient, but we kind of need it to do that. But holding the head pressure down is a good thing, no matter what, right? Like, we do not want elevated head pressure for no reason. So when a condenser coil, let's do something that's specific to your market. When a condenser coil is in the salt air and all the fins fall off and there's just tubes left, what happens to your head pressure? It goes up really high, right? Because why? Because you're not able to get the heat out of that condenser. The condenser is the heat rejector. We want to get heat out of it. If you can't get heat out of it and the heat stays in it, what happens to your head pressure? It stays up, right? Hotter condenser equals higher head pressure, right? And we don't want that. Why? Because of this reason. Higher compression ratio, higher difference between suction and head, because your evap temperature still needs to stay the same. Head pressure goes up, that's a higher compression ratio. Compressor runs hot, oil breaks down, nothing works great. Power bills go up, capacity of the system goes down, everything sucks on the system. So we want to keep our head pressure as low as we can, really. There's no reason not to, as long as we're still producing the subcooling that we're looking for, that liquid. So what is that number, okay? So here we say 15 to 20 degrees saturation above outdoor temperature. So what that means is our condensing temperature for older systems, more traditional systems, is going to be 15 to 20 degrees above the outdoor temperature. So let's do the math here. Let's say it's 85 degrees outside. That's pretty typical here in the summer. What is our what is our condensing temperature going to be? Yeah, 85, so 100 to 105, right? Did I say that right? Yes, 100 to 105, no, yes, 100 to 105. You see how bad I am at math. That's what our condensing temperature is going to be on a, not super high efficiency system. For super high efficiency systems, we can get all the way down to 12 or 13 in some cases, right? So you may see on a really big condenser, 85 degrees plus 12, you may be 97 degree condensing temperature in some cases. Is that what you guys are seeing or no? Is that about what you're seeing, or is it even lower than that? It's right in there, okay, all right. That's going to be typical for a high efficiency system. So when you go up to a system and you're looking at your condensing temperature and it's significantly higher than that, what do you know? You know something ain't right, right? I was looking for simple here. You know something ain't right? To talk like the Groveland guys who I grew up with. Something's acting weird here, right? And so you got to couple that together with other information. But to Jerry's point, it's almost always a dirty condenser. Like that's really what you're looking for. Go ahead. What's that? Could be an old condenser, right? The fins are falling off. It's in really bad shape, right? You can't always clean these things to perfection, especially in salt air. But it's having a heat transfer issue out of the condenser. That's really what it's telling us. We're not getting the heat out of that condenser. There's some other weird possible causes. Say somebody went and they swapped a condenser fan motor, and they put the wrong RPM in. Somebody swapped a 1075 with an 825, right? It could be somebody put a new motor in, and they got the fan blade in the wrong position in the shroud. Right? They have it sitting too low in the shroud. Now it's just sitting there beating air around and it's not moving the air out properly. There's a lot of possible things that could cause it, but generally speaking, it's either coil's falling apart or it needs washed. That's your typical cause of that. So that's good. Good information, right? Helpful to know. But it's condensing temperature. Now here's a neat thing. What would be a way that you could pretty much figure out condensing temperature without using gauges at all? You could use a thermal camera, right? If you look at it, now thermal cameras aren't great in terms of accuracy when you're looking at a reflective surface like a condenser coil. So it's not going to be perfect. But one of the things that's kind of fun with thermal cameras, if you're on a site that has more than one unit, thermal cameras are really good at comparing, right? So you can go like, how's this one look? How's that one look? Whoa, that one's hot, right? That one's a little higher temperature. And you can also see subcooling with a thermal camera. If you look at it and you can see the coil, now again, if it's like a train and it's got the armor on it, good luck. It's going to be hard. But if you can see the coil and you look at it at the thermal camera, you can actually see those bottom rows dropping in temperature, and that's subcooling. Because you're going to see real hot at the top, you're going to see the same temperature in the middle, and then you're going to see the subcooling down at the bottom. And if you don't see that, where it's all the same temperature, all the way out to the liquid line, indication that you don't have subcooling. Right now, would you do that? No, you would just use your temperature clamps. And we talk about a little bit more about non-invasive, if we get to that, which I hope we do, we'll cover that even more. Bunch of different possible causes. All right, superheat. Again, what does superheat tell us? When we measure superheat and we get a number, we have 5 degrees of superheat. What does that tell us? Say that? It's additional heat that's being absorbed after saturation, after it's done boiling. So it's no longer a mix, now it's being added. Here's the way I want you to think about superheat though, which I think will make it a lot easier for you when you're trying to compare. We know what coil temperature, we know suction pressure is coil temperature, right? So that tells us how cold the coil is. Superheat tells us how full the coil is. Saturation, suction tells us how cold it is, and superheat tells us how full it is. So a high superheat number, so let's say you're 30 degrees of superheat. What does that tell us about how full the coil is? Tells us it's less full, right? So if we have high superheat, that means that this boiling refrigerant is only making it so far up the coil, and then the rest is sensible. The rest is added after it's boiled. Let's say we have 0 superheat. What does that tell us about how full the coil is? It tells us it's completely full. Completely full, overfull, right? But it's full all the way to the top. We don't want it to be full all the way to the top. That's not good. We want the top little bit to be fully boiled, and now it's picking up temperature when it's fully vapor. So when you start to think about that, temperature and fullness, that's kind of the whole story, right? Now, I want to be very careful with these measurements. Because where do we measure superheat? Where do we typically measure it? We measure it outside, right? Is that what we're actually trying to find out, is what our superheat is outside? Where do we care about what our superheat is? Right, we care about fullness at the evaporator coil. We care how full it is at the evaporator coil. So if it's a 150-foot line set and somebody didn't insulate it and ran it underground for 20 feet, that really tells us nothing at that point about what's going on at the evaporator coil. Now, do we care about it? Do we care about what the superheat is outside? Yes, we do, for another reason, which is what? Somebody said it. How much heat is being up before it hits the compressor, which we care about for... Well, yeah, it's a heat that you now have to reject, right? So that's going to drive up your head pressure unneededly. Because now we have to reject this additional heat. That's not cool. Literally not cool, get it? No, that's not a good joke. We're not going to do that joke. No, not going to happen. So that's not good, but it's also really bad for the compressor, right? The compressor needs cool suction gas coming back to it. So these compressors are cooled by what? Refrigerant vapor, right? They are not air-cooled compressors. The air, and you know this because like a lot of the compressors that you see, especially on these fancy, they have jackets all over them. They have a coat on them. And when I first saw that, I was like, oh man, that's going to make the compressor overheat. No, it's not, right? Because it's got this cool vapor going into it. That's what's supposed to keep the compressor cool, not the air around the compressor. So it's a refrigerant-cooled compressor. If that refrigerant isn't cool because the suction line isn't properly insulated or it's way too long or whatever the case may be, that's a problem. So we do care what the superheat is outside, but for a different reason. Now, if the line set's only 15 feet, 20, 25 feet long, we kind of know, right? We know that it's going to be pretty much the same temperature inside as it is outside in almost every case, right? So we can kind of go with that. But when in doubt, if you want to see, if you're seeing a high superheat and you suspect, maybe it's because of how long it is, what do you do?
Check the temperature inside.
You take your clamp, because you're measuring out there at the condenser, okay, you're like, oh man, my superheat's 25. That's not great. What do you do next? Take your clamp, look at what the temperature is. Okay, well this is saying 65 degrees, okay. So now I'm gonna go inside, and I'm gonna measure it there, and I'm gonna see that it is 55 degrees there. Oh, okay, well, it's just picking up that much superheat in the suction line. Now, is that good? No, but I can't do anything about it other than reinsulate the suction line or something. You know, like there's not going to be a great solution to that at this point. If I go inside and it's 25 degrees superheat on the inside and it's a TXV, now I'm like, oh, okay, this TXV is underfeeding. Something's going on with this valve, or it's a restricted, biflow dryer or whatever. There's a kink or something else. There's gunk in the screen, whatever. Make sense? So we have to always, and again, you have to stack information and information. When you look at the 5 pillars, they only work if your temperature clamp is reading properly, your pressure probe is reading properly. You know that it could be different inside or outside. Same thing's true of the liquid line, right? You ever walk up to a system, you get it charged, you know it's working right, everything's great. You walk inside and you hear, right? Stop. There's a problem. If you have flash gas going in your liquid line inside, I don't care if your subcool is dialed in on the outside and your superheat looks fine out there. I care about that flash gas. Why is it doing that? Why is that happening? Is it because there's a restriction before it, or is it because maybe it's missized where they got a different size copper under the platform or something, or maybe it's that it's just run too long. Maybe it's just way too far, or maybe it's running through an attic or something and it's gaining heat there, but it's getting back to flash gas before it hits the metering device. That system's not going to work right in that case. In some cases, you may actually need to add a few more degrees of subcooling in order to get that, in order to eliminate that flash gas at your metering device. Again, if there's nothing else wrong and it's not something you can't fix.
Because at all times you want a full column of liquid going to the expansion of that.
Correct. And this is one of the main things. And again, this goes back to troubleshooting. Who here has ever condemned a bad TXV in their career? It's bad TXV, right? Who here has ever misdiagnosed a bad TXV? Where you said that it was bad and then you put a new one in and it wasn't actually bad, right? Right here, right? All of us have done it. And what is it usually when we troubleshoot a bad TXV and we're wrong about it? It's either that there's another restriction that wasn't the TXV, right? It was a flash gas issue. We weren't feeding the valve with a full column of liquid in the first place, because that's what you have to do. Or it was an airflow problem. And we were just saying, oh, my suction pressure's low, and so it's probably the valve. Valve slamming down.
Yeah, sometimes they can have like a mix match unit, like they have a 410 condenser with a 22
Right.
evap, so you have to take note of everything.
Absolutely. If they have the wrong refrigerant in it, something like that too, that could be. You know, like if somebody could have put something else weird in it.
Hey, what about when you run into, we don't see it often, but sometimes we'll see a 1/2-inch liquid line on residential equipment.
A 1/2-inch liquid line on residential equipment. Yeah, and what'll happen when you have a liquid line that's too large, that's not a good thing. you're going to have a lot of extra refrigerant in that system. And so when you go to charge it, it's going to, like, getting subcool is going to be really hard. And then in order to get proper subcool, you're going to have to add a lot of refrigerant, which is going to be very risky for the compressor. Because now in the off cycle, like we talked about yesterday, it's very likely that you're going to get refrigerant condensing in the compressor in the off cycle if you don't have other things in place, right? So you could do something like an off-cycle solenoid, crankcase heater, other things to mitigate that. But it's not good for the compressor when you have more refrigerant than that system was designed to have in it. Does that make sense? So a lot of guys will be like, too big a liquid line, that doesn't matter. All that does is just results in lower pressure drop across the liquid line. No, it results in a heck of a lot more refrigerant in the system. Here's a fun fact. This is just a side note, so this is kind of for you and some of the other senior guys here. Let's say you have condenser on the roof, evaporator coil really low. No, and the answer is if you start to look at manufacturer data, you'll see that in a lot of cases you can downsize your liquid line. Because this is something called static regain, and this is a really weird thing. You will have higher pressure at the bottom than you do at the top, because you have a column of liquid. So gravity is actually working for you in that case. So in some cases you can go down to like even a 1/4 inch liquid line on a typical system, and it will still function just fine because of that static regain. Now, why would you do that? Well, the argument is that you could actually put less refrigerant in the system and now have less risk of issues potentially with that. Now again, that's not probably realistic, but you have to think about that separation. If it was going the other way, you potentially might need to, because you actually get pressure loss as you go up the tube. Knowing your superheat. Superheat comes down to what type of metering device you have. It's really important to know what type of metering device you have. And nowadays, do you guys see many piston systems, fixed metering device systems anymore? Still a few of them, yeah. We see a few of them now and again. And that's where, like a lot of new people, if you went to school, you were taught you charge the system by superheat when it's a fixed metering device or when it's a piston system. That's what they would say. But again, I don't like to focus on how you charge the system, right? How you charge the system is by however the manufacturer tells you to charge it. That's not what we're talking about here. We're talking about how do you know what everything should be. Like, how can you tell if the whole system is working properly?
What they say, sometimes they say, for orifice, you charge for superheat, and for expansion valve, you charge for
subcooling, yeah. Yeah, they say that, and again, that isn't false, that's true, but I'm less concerned about how you set the charge. I'm more concerned about how do you confirm that everything else is working properly, right? So it's not just a matter of setting charge, that is important, and with the apprentices, we're going to talk about that, right? How to set charge by superheat or subcool. But what's more important is the performance of the equipment. It's more important all of these different measurements that you have to take, and are they all within the proper range, right? What you would expect, seeing something that's not quite right and being able to notice it. Because that's not the only issue you could face. But just so we understand the rules of thumb, for a TXV system is 10 plus or minus 5 is your typical operating range. Now, you're very rarely going to see 5 degrees of superheat. That would be very abnormal in the world that we work in, especially outside where we measure it. You will see it sometimes at the inside. But there are actually a lot of manufacturers, and we see this a lot with Carrier, where the valve is actually setting superheats that are too low, and they will actually go down to 0 superheat. And in a lot of cases, it's just because of how the bulb is positioned, how the bulb is insulated from the factory. So in a lot of cases, I've had to go in and actually insulate a factory bulb in order to get that superheat where it needs to be, right? It's because the ambient air is affecting it and driving the valve too far open. So that is something to pay attention to. That's why, even though you set your subcooling on a TXV system, that's how you set the charge, that's how you know, I also want you checking superheat. Because if your superheat's too low or your superheat's too high, that's still something you need to pay attention to. You need to know. If you set the charge by subcool, but your superheat's 30, that's not great. That's a potential problem, right? If you set your charge by subcool and your superheat's 0, that's still a problem. You have liquid refrigerant coming back down. So I still want you to understand what those measurements mean. And the same thing is true with a fixed metering device system. If you have a piston system and you're charging it by superheat, I still want you to measure the subcool. I still want you to know that you have a full column of liquid in the liquid line. It's important to know that. That's the 5 pillars. Make sense? Okay. Probable causes of improper superheat, it's like basically everything. But you first have to know which type of metering device you have. And again, if it's a TXV or an electronic expansion valve, it's typically going to be the same sorts of things. Making sure, and again, like when we are troubleshooting a TXV or you're troubleshooting an electronic expansion valve, those are what I call constant superheat valves. Their job is to set the superheat. Their job is not to set the pressure. So a lot of newer techs, when they see that valve, they imagine that the job of that valve is to get the pressure to the right level in the evaporator. It's not. It doesn't care what the pressure is, it cares what the superheat is. So if it sees that you have zero superheat, it's going to start throttling back refrigerant into that evaporator coil. Matt calls it like a shower head. If you imagine, like it's like a shower head, like spraying refrigerant into the coil, right? And he sprays it into the coil, and then it boils up. If it's seeing zero superheat at the top, it just throttles back how much refrigerant it's putting in until that superheat gets in range. If the superheat gets too high, then it puts more in. And again, that's where it's really helpful to think about superheat as fullness of the coil, right? And so the TXV or electronic expansion valve is modulating the fullness of that coil. It's not modulating the pressure in the coil. That's not its job, right? Pressure is dictated by load. If you have low airflow, you're going to have low pressure in the coil. You just are. If it's really cold in the house, you're going to have low pressure in the coil. You just are, right? Is there other ways to compensate for that? Sure, but don't do it, right? It'll cause other issues. So when you go up to a system and you know, hey, I've got the proper subcool, I know the thing's charged right, but my coil temperature's low, what does that tell me? I know it's off in airflow, right? I still need to look at superheat. All right, setting the superheat right so I know the valve's working. I know I have a solid column of liquid going to the valve because I have the proper subcooling. My suction pressure's low, my evaporator temperature's low. It's probably airflow, right? Because I know the indoor conditions. So again, if I walk into the house and it's 60 degrees in the house, okay, well then I know, right? Like that's not hard to know that. So it's probably airflow. And in most cases, it's airflow with that, when you see that low coil temperature, if you've done the other pillars. All right, subcooling. We've already talked about this. Subcooling, again, for a TXV, and really most systems that you work on, is going to be 10 degrees plus or minus 3. Now, again, it's easy to know what your subcooling should be because you just look on the condenser and it tells you what it should be in most cases. There are some microchannel condensers that do have a range of subcooling based on conditions. Okay, so you do need to pay attention to that. But most cases, it's just the number that you're trying to hit. So really, realistically, if you know your airflow is generally right and everything's set up and it's running and you're weighing it in and all that stuff, you really are just setting your charge to subcooling. You're adding in order to increase the number, you're removing to decrease the number. That's mostly what you're doing there. And even if your airflow is not perfect, subcooling will still pretty much be okay. It'll still be in the same range. That's an argument that Jim and I have, and we talked about this a little bit yesterday. With some of the apprentices, or I don't remember who it was, but like, can you tell if your airflow is good based on your refrigerant pressures? And the answer is, yeah, sorta. Like you can kind of tell. I mean, if you have a system where everything else, all of your 5 pillars are lining up, and your suction saturation temperature, your evap temperature is just low, yeah, that's an indication of low airflow. And if it's in proper range, it's a pretty good indication that your airflow is pretty good over the evaporator coil. But you have to use those in conjunction with each other.
We haven't reached here, but can your static pressure readings be good, but you have bad airflow?
Yes, absolutely. Matt's going to talk about this, but since you asked the question, it's very important that you know this. First off, we're assuming that you're measuring it right, like you're putting it in the right spots. Especially when you're dealing with a newer tech, that's not a good assumption to make, right? You really care about what it is at the blower. We say total external static, but really what we care about is what it is right at the blower, right? That's actually what matters. It's because if you have a dirty evaporator coil and you're measuring it external, yeah, you could have great static pressure in a filthy evaporator, right? And that doesn't mean you have good airflow. But the most important thing is that system baseline producing the right amount of airflow? So what is static pressure? It's right in the name. Is it a measurement of flow? Is it static flow? No, it's pressure. It's just pressure. It's telling you what the pressure is. And the pressure is dictated by the amount of air that's being moved in the first place, right? So it's kind of another one of these chicken and egg problems. It's like, Well, my static pressure is good. Well, do you have good airflow? Well, I'm using static pressure to figure out if I have good airflow. Oh, right? It's a little bit of an issue. And so if you have a system that the fan speed is set wrong, if you have a system that somebody put some weird blower motor in it that's not the right one, somebody put a blower wheel in it that's not the right one, the blower wheel has crap all over it and it's not moving the right amount of air, yeah, your static pressure will look fine and you will have almost no airflow. Right? A good example would be, you've all seen a really dirty blower wheel before, like where it's just completely crusty crudded. If you go up to that system and you measure static pressure, it's going to be really low. It's going to look great. Why? Because, right, I'm going to use another example of this, okay, because this actually comes up sometimes with some train units where they'll show a low superheat code. What is the superheat of a system that is not running? Zero superheat. If the compressor's not running, you have zero superheat. Why? Because the temperature of the line and the pressure are the same, right? Our condensing temperature and the correlating temperature on the pressure scale is the same. So we have zero superheat. What's our subcool? Zero. Well, if you follow what I'm telling you, zero superheat tells you have an overfed evaporator coil. None of that applies if the compressor's not running, right? None of this makes any sense if you don't have the primary heart doing what it's supposed to do. And that's where a lot of guys get really confused, because let's go back to compression ratio. Let's go back to this. What is the compression ratio of a system that's completely off? It's 1, right? It's 1 to 1. They're the same number. Wow, that's a really efficient compressor. Right? And the answer is yes, it is. It is a very efficient compressor because it's not doing anything, right? And you're not putting any power in, right? So a lot of this stuff, everything that we do that's pressure related, because that's what we're doing. All these calculations we're doing on the air side and on the refrigerant side are pressure related measurements. They rely on a properly functioning heart. And if that heart isn't properly functioning, all bets are off. Now, we can say, look, my compression ratio is really low, like really low. That's an indication of a compressor that's not pumping properly. That's how you actually tell. Like, oh, I don't think this thing's pumping. You listen to it, amperage, everything's like, yeah, this thing's not pumping. Same thing is true of the blower, though. If your blower's not pumping, if it's not moving enough air, your pressures are going to be really low because it's not moving. Go ahead.
This is what I'm trying to say about don't technician confused when I'm diagnostic by the expansion valve, if it's the compressor not pumping right or something.
Yeah. Yeah.
Nobody pay attention too much to the compressor not pumping because it's running now. They say, well.
Right. It's running. Right. Exactly. They're like, it's running, so yeah. Yeah, and that's actually, and I want to do, and if we can get to it, I want to do a whole section on compressor troubleshooting because it's one of the more misunderstood things. Whenever you have this case, now again, you guys have the advantage that you don't have to deal with reversing valves. In our market, a reversing valve that's bleeding through looks exactly like a compressor that's not pumping because it is basically a compressor that's not pumping. It's really hard to tell. It's pretty easy to tell if it's a metering device wide open or a compressor not pumping. That's not that hard to tell, right? So in both cases, you're going to have a lower compression ratio, but in most cases, a compressor not pumping is going to be significantly lower compression ratio. Like a valve that's wide open, right? You're going to have zero superheat, and the unit's still going to be working, right? It's still going to be producing pretty decent capacity in almost every case, because that valve can only open so far, right? Like even when it's fully open, it's still doing a decent job of metering. You're going to have a high evaporator temperature in many cases. You're not going to be dehumidifying very well, but it's not going to be the valve. In most cases, when you see really low compression ratios, really high suction, really low head, it's usually the compressor not pumping. Now, before the junior guys just, hey, got a bad compressor, swap it out, right? Well, what's the mistake there? I'm going to let the senior guys dictate that. Well, bad compressor, swap it out, not pumping. What's the mistake? What do you need to do first? What? Well, you already did that, and you said it's not pumping. You got to let the thing shut it off, right? Let it equalize, because it probably is out on bypass. It probably had really high head pressure or something, some really high compression ratio, and it went into bypass. Have you ever tried to pump down a scroll compressor nowadays? Try to pump it down. What happens when you get down? right? It unseats to protect itself, and then it just goes into bypass, right? Have you ever had a scroll compressor run backwards in residential? LG scrolls, they love to run backwards. You short cycle them, and they start making a crazy noise, and they don't do anything. And a tech goes, oh, bad compressor, put a new one in. Some of them, yeah, rotary compressors can do the same thing. So shut it down, let it calm down, and then restart it, right? And then in many cases it runs just fine. In a lot of cases, the reason why that happens is because somebody short cycled it. Like they jiggled a float switch, and it kind of like it shut off and turned on real quick, and it moved backwards, and then it starts spinning backwards on you, right? Same thing is true, like I said, if you have really high head pressure, you got a condenser that's coming apart, somebody put way too much refrigerant in it, whatever, it goes into bypass, or they tried to pump it down, it goes into bypass. It takes it a little bit to reset, right? So you've got to let that happen. So a lot of times compressor's not pumping is not because the compressor's broken, it's because it has an internal safety that is causing it to bypass so that way it doesn't damage itself, right? Make sense? So I know I did a weird little thing there where you asked me a question and I went all these weird directions, but the reason I did that is because I'm a very weird person and I have mental problems. No, the reason I did that is because this is a first principle, like you guys were talking about, a first principle of troubleshooting. Before you can look at pressures and they mean anything, you have to know to pretty good confidence, is the heart working? If the heart's not pumping, compressor, if the heart's not blowing air through the system at the proper amount, then the pressures mean nothing, right? And that's where using your senses can be really helpful. If you walk up to a condensing unit and you can hear psh, or the compressor just sounds crazy. It sounds like a bag of hammers shaking around. Like, and you see the new guy, okay, let me check my superheat and subcool, you know, like, hey there, guys. Yeah, I know everything's working fine, ma'am. You know, like, right? It's like, stop. Why does it sound like a bag of hammers? You know, like, what is happening right now? Why is it going psh all the time, right? It's in bypass. It's running backwards. Something's happening. Weird. Like, just stop and deal with that first. Same thing with your blower. You walk up to a unit, and this thing, you know it's in high stage, or at least it's supposed to be, and you walk up and you can't hear it running. Like it's barely running, and you're used to these units. You work on them all the time. You know there's always a little whistle or a little, you know, like you can hear the thing, and you don't hear anything. The return's quiet, right? Like maybe we're not moving the right amount of air. Maybe it isn't set up right on the control. Maybe the pins aren't set up right. Maybe it's PSC motor and it's not on the right speed tap. I don't know, something.
Yeah, I have a question. I recently, when you mentioned about the bypass, right? I recently went on a system, like a compressor. That was making noise. The pressure is good. Everything is okay. Making noise. Check the system, pumping on the system. Going to that bypass. What would cause it?
So it was making noise initially. It was making noise, but it was working okay. You went to pump it down, and then it went into bypass. Yeah, and again, like what it sounds like is probably happening there is that you had a bypass that was a little bit stuck open. Like it wasn't fully open, but just a little bit, enough to make a noise that you could hear. A lot of scroll compressors will bypass when you pump them down. That's just, and it depends on the brand. Like every brand's a little different, every model's a little different. So Copeland compressors, Copeland scrolls nowadays, when you get them down to a certain level, they just bypass, and it's a compression ratio thing. So again, when you think about compression ratio, if your suction pressure is low, what does that do to the compression ratio? It makes it bigger, right? And when you pump that thing down, is the suction pressure low or high? No, it's low, right? You're pumping it down. So yeah, because, correct, your suction gas is getting lower and lower, right? Lower and lower pressure coming into it. And so that compressor's designed, when the compression ratio gets too big, it just goes into bypass. So it doesn't damage itself. So it stinks, right? So you got to kind of know. So what you do next time is like, all right, it went into bypass at, let's say, 30 psi, 40 psi, 50 psi. That's where it went to bypass. So then you stop before that next time.
Question.
Yeah.
What is the difference in diagnosing a compressor at standing pressure versus operating pressure?
Say that again.
Diagnosing a compressor at standing pressure.
Right, static pressure is off.
Standing pressure is off.
Yeah, right.
Versus operating pressure.
Operating pressure is like it's running.
Yeah.
What are you diagnosing in that case?
But I heard a lot. Oh, my standing pressure is this.
Right. Oh, right. Okay, I see what you're saying. Right. Yeah. People. Right. People will say, Yeah, my pressures are yeah, they're low, they're high, they're whatever. Okay, they're the same. Was it running? No. Well, then what does that mean? It means nothing, tells me nothing, right? The only thing it could possibly tell you is if you're completely flat. Like, so if you walk up to a 410A system, you hook up, the thing's off, and you're running 80 PSI suction in liquid, well, yeah, it's got no liquid in it whatsoever. It's at vapor pressure at that point, meaning you have no liquid. Well, yeah, it's flat, right? So sure, that means something. But other than that, static pressure doesn't tell you anything. When I say static pressure, standing pressure system is off, right? Your refrigerant pressures tell you nothing at that point. Yeah, good point, good question.
Thanks for watching. If you're willing, give this video a thumbs up and drop us a comment. Don't forget to hit that bell icon to stay updated with all of our future videos. And as a quick reminder, HVAC School isn't just a YouTube channel. Dive deeper with us at our main website, hvacrschool.com. Curious for more knowledge on the go? We've got you covered. Tune into the HVAC School podcast, available on all your favorite podcast apps. And while you're at it, join our thriving Facebook group. Also, don't miss out on our free mobile applications available for both iPhone and Android. We're all about community. For techs, by techs.